Okay, so this is going to be Physics 111, Chapter 13, which is going to be gravitation. So, when we think about gravitation or gravity, okay, we mainly think about the famous, it's not writing. Here it is. The famous apple on a tree where it falls down on Newton's, which is not a true story. It's kind of fabricated for a kid's tale. What it was, Newton came in, and here's, let me just try to put this apple in red. Okay, so Newton came in, and he was observing the apple, and he was wondering, why is the apple falling down? And he gave the answer of gravity. So Newton determined that there was a force, that the force is going to equal to some kind of constant multiplied by the first mass of the first object multiplied by the second mass divided by r squared. Now the mass that he's trying to determine is mass of the Earth. Earth. And r is the distance between the two objects. Distance between the two objects which is in this case from the Earth to object. So F will be the force between the both objects. Now he knew there was a G, which is going to be a constant, a gravitational constant. Which he knew it was very small. But he didn't know how much exactly it was, which we already know is 6.67 by 10 to the negative 11 Newton meter per kilogram. But why is that? Well, it was until this English physicist came. His name is Harry. Sorry, it's Henry. Henry Cavendish in 1798. He was the first to determine this gravitational constant. The gravitational constant, G. He did this little experiment where he had, let me just throw this little bar over here, a little bar in there, and in there he had a wire that's connected by a rod of length L. And on that rod, he has two small masses. I'm going to call them M1 and M2. Now, he got two big spherical, let me get a different color, spherical balls close to it. So you got one big one over here, one big one over here. If I'm not mistaken, they were about 167 kilograms, which M1 was about close to 5 kilograms, if I'm not mistaken. So now what you notice is you're going to have your force, your angular acceleration is going to turn into angular momentum, L. Now this is the length L, and you're getting angular momentum. Now your wire is going to go turn on the other side. So you get a small, so A and B are small masses, at length L, suspended from a ceiling. Now you got two large spheres, which we're gonna call S1 and S2. So S1 and S2 that are brought close, to the small spheres. Two small spheres. Now, again, what he's seen was that your S1, and we're going to call them the S2, attracted, let's call this A and B. Except M1 and M2, A and B. Yeah, I like that better. So your S1 and S2 attracted A and B by equal and opposite growing force. Let me just open this. Now, what this happened, this gave rise to gravitational torque. Which is F into the angular momentum. Now, the wire was twisted at angle theta. And think of it this way, right? So suppose if you had the headphones, the big old headphones, kind of headphones, and you suspended from your finger with the headphones up, right, with the wire. If you actually turn the headphones around, what's going to happen afterward? That the wire is going to actually try to free itself with angular momentum and go back to its original shape, right? So the wire was twisted at the angle theta. So what he said was, okay, so you got a torque multiplied by an angle that you have, which is going to be our force multiplied by your length. And he defined the gravitational constant as your torque multiplied by theta multiplied by d squared divided by your first mass multiplied by your second mass multiplied by L, the angular momentum. Now, D was the distance between the small and the large spheres. Now, the number that he got, and I'm not going to get into the whole math of this, but the number that he got was 6.74 times 10 negative 11 Newton meter per kilogram. Newton meter square per kilogram. Square. Now, the number has been recalculated since then. And he was just 1% off. Which we actually used the G once this was recalculated as, and I'm just going to write it in green over here, 6.67 times 10 to the negative 11 Newton meter square per kilogram square. So Henry Cavendish, he's the first one who actually determined what G was to be used in the formula that Newton actually developed. So let's say if you have a object. No. So basically, before we do that, your formula was, your gravitational force formula was G, F equal G M1 M2 divided by R squared. Now, again, taking the mass of the Earth, we should write that down. Mass of Earth, which is 5.97 times 10 to the 24 kilograms. The mass of the Earth is big, right? So you measure the Earth as 5.97 times 10 to the 24 kilograms. So you want to see the force between you and the Earth. So we're using the mass of the Earth for M2. And for R, we're using the radius of the Earth. Which the radius of the Earth is 3,958.8 miles, which is, if you convert it into kilometers, is 6,371 kilometers. So basically, you got a constant of G that Henry said it was 6.67. That we determined it was 6.67 times 10 negative 11 kilogram meter square per, Newton meter square per kilogram square. So you got three constants going on, your G, your M2, and your R squared. So let's rewrite the formula. The only one we don't have is M1. So F equals M1. So G M2 divided by R squared, which if you actually calculate all three of those, you're going to get an acceleration. Well, let's go ahead and calculate it. Go ahead and calculate this. So your G M2 over R squared, which is your gravitational constant, multiplied by the mass of the Earth, divided by your radius of the Earth, squared. So multiplying the first one, which is your 6.67 times 10 negative 11, multiply that by 5.97 times 10 to the 24. Divide that by your 6371 times 10 to the 3 power square. Which, once I got in my calculator, I got 39.83 times 10 to the 13. Divide that by 405. 8964 times 10 to the 6th power. Divide those two, and what we get? Almost 9.8 meters per second square. So that, what we get, your low gravitational constant, G, which is your gravitational constant for gravity, which is the average is 9.8 meters per second square. Now, obviously, it's not going to be like that all over. So, if you actually go on the highest mountain, like let's say you go in Mount, let's say you get a balloon, you go in a high space, your gravity will fall down. Your gravitational constant will fall down below 9.8. The more you go towards the Earth's surface, the more gravitational constant you're going to get bigger. So your G is 9.8. And so your force is your gravitational constant G multiplied by your mass. Sorry, let me just write this down backwards. Your mass multiplied by your acceleration, which is your mass multiplied by your G. So let's say, okay, let's say, I'm like sitting right over here and on the world, this is the Earth. Now I weigh, I don't know, let's say 70 kilograms. Well, according to what we're saying, that there's a force, gravitational force, between me and the Earth. That means I'm going towards the Earth in a gravitational force. Why is not the Earth going towards me in a gravitational force? Well, let's look at that. So we said that the force equals your gravitational force equals your mass times your gravity, acceleration for gravity. So that means your force, in this case, is going to equal to your mass, which is 70 kilograms, let's say, multiplied by 9.8. Which if you calculate it, you get 686 newtons. Now, so let's look at it from the person on the Earth or from the Earth point of view. So your force is going to equal your mass times your acceleration, which is your mass multiplied by, well, hold on. Let me just do this. So your force equals your mass times your acceleration. So that means for the person, our force, again, was 686 Fg, so that's 686 equal for the person, which our mass was 70 kilograms again, equals 70 kilograms multiply that by your acceleration, A. That means your acceleration is going to be what? Almost 9.8 meters per second square. Now let's look at it from the Earth point of view. Your force, again, is 668 newtons. That's exerted on the object. Is going to equal to your mass of the Earth. So at this point, it's going to be your mass of the Earth, and this is mass of the person. I'm just going to call it MP. So your mass of the Earth, again, we defined it as 5.97 times 10 to the 24 kilograms. So this is going to be 5.97 times 10 to the 24 kilograms multiplied by acceleration, A. Again, this is a very, very big number. So in this case, A is going to equal this really big number. Your 5.97 times 10 to the 24, divide that by 686. And it's going to be really, really, really very, very small. That is unnoticeable. So let's say if you have an object. So let's say you got an object of, let me just draw better than that. So let's say if you have an object of mass m that is taken up right over here for a distance of, I don't know, delta y. Now your gravitational potential energy for that, let me actually get blue. I like blue. So your gravitational potential energy for G, delta VG. Now we're going to follow your book. We're just going to go U of G. Okay? So that's your potential energy again. I have two, yeah. Energy. Okay. Now that's going to equal to your mass, and we saw this before, multiplied by your gravitational constant G multiplied by your displacement, delta y. Now again, we mentioned that G was a resultant of your gravitational constant multiplied by your mass of the Earth, which we're going to call M2 divided by, we call this R, or R squared. That means your gravitational constant, your potential gravitational energy for G is going to equal to your mass, which I'm going to call, this is the same mass over here, right? So I'm going to call this M1. Multiplied by your G, which is your G gravitational constant multiplied by mass 2 divided by R squared, multiplied by your distance, delta y, which is from radius to radius, R. And again, your R, I'm just going to write it down over here, your distance between the objects. Now, here's the thing, right? So looking at this, if you notice, we have two R's, so one of the R's cancel out. Let me actually use a different color. One different R's cancel out, so that means your gravitational constant, your gravitational potential energy, is going to equal to M1 multiplied by G, M2 over R. So notice that as R gets larger, let me just write this down. The gravitational field goes to 0. Right? So if R goes up bigger and bigger and bigger, your potential energy is going to go smaller, 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 and eventually to 0. But here's the thing, right? When your gravitational goes, when your R comes up, that means your potential gravitational energy goes down. Your potential gravitational energy goes down to 0, but the further you are, you're supposed to have larger potential energy. So we actually include a minus or a negative on it because the further you go away, the higher potential energy you should have. Potential energy you should have. And that's where we go from the negative. So it goes from a big negative number until it reaches to a 0. So it goes down to a 0. So that way your potential energy is actually greater when you're actually having more distance. So we said that, let me just write this down, new page. So we said that, so your gravitational force is going to equal again to G, your gravitational constant, M1, M2 over R squared, where the gravitational gravity is your G multiplied by M2 divided by R squared, which actually define this as the mass of the Earth and the radius of the Earth, and the gravitational potential energy is going to be minus G M1 M2 divided by R. So we're talking about, again, having this force between the Earth and the person, right? Or whatever object it is. So the density, which again equals your mass per volume, let me just write this down. Is going to equal to the mass, and I'm going to use big mass, of the inside of the Earth, I'm just going to get INS, inside of the Earth, divided by its volume, which is Earth's sphere. So the volume of the sphere is 4/3 pi r cubed, which is going to equal to the mass of the object, of the Earth itself, divided by 4/3. Why is it not writing? I hate this. Pi r cube. Now, looking at this one, let me just rewrite the equation down. Okay. So, your mass of inside the Earth divided by 4/3 pi r cubed is going to equal to your mass divided by, again, 4/3 pi r cubed from your density, which you can cancel out your 4 over 3 pi. So really, your mass inside the Earth is going to equal to your mass. Hold on, let me just, my pen stopped working 1 second. Okay, I had to go change the pen. My first pen stopped working. So where were we at? All right. So taking the 4 over 3 pi, we had pi r square over here, r cube, I mean, because it's volume. So that we add the mass of the inside the Earth is going to equal to your mass divided by let's call mass of the Earth R, big R. Let me write the whole thing back. All right. So let me write the whole thing. My pen was not working, so it was cutting off some stuff I was writing. So let me rewrite the whole thing again. So you got your mass of the inside the Earth is going to equal to your 4 over 3 pi r squared. Now again, r is your distance. It's going to equal to your mass divided by your 4 pi. This is going to be affected by the radius, and I'm just going to give it r cube. I'm sorry, this is supposed to be r cube. This is going to be r cube, and this is going to be your Earth radius. Now, that means your mass of the inside of the Earth is going to be, and again, your 4, I forgot the 3, 4 over 3. Your 4 over 3 pi cancel out. So what you have is your mass of the Earth divided by r cube, which is going to equal your mass divided by r, mass of the Earth cube, radius of the Earth cube, which means that your mass of the Earth, of inside of the Earth, is your r cube, your big M divided by r cube. Now your F, your force, is your that gravity multiplied by your mass multiplied by your mass inside of the Earth divided by r squared, which is going to equal to your gravitational force multiplied by your mass of the Earth. Let me just write this down. Mass of the Earth multiplied by r cube divided by r squared multiplied by r cube. Again, this one's going to cancel with this one. So what you're going to have is your force is going to equal to Gm, big M over r cube. Now, if you multiply the constants all together that you have, oh, I forgot the r, multiply by an r. Now, if you multiply all the constants together, you're going to get a constant k. So if you include the mass of the Earth, the radius, the gravitational force plus the mass of the object, you're going to get a constant k, which this is going to equal to minus kr, which is your Hooke's law. Now your mechanical energy, when you have a satellite, for instance, going around the orbit, so your energy, your mechanical energy, is going to be equal to your kinetic energy plus your potential energy, which is going to equal to your 1/2 mv squared plus your potential gravitational energy, which is, I'm just going to say it's U, which is, to follow your book, 1/2 mv squared plus minus g m1 m2 over r. Now all of that is going to have to equal to 0. That means your 1/2 mv squared is going to equal to g m1 m2 divided by r. Let's call this one m1 for your first mass. Solving for the velocity, you're going to get g m2 multiplied by 2 divided by the radius of the Earth, r. And that's, ladies and gentlemen, what you get the escape speed for satellite out of orbit. So if you actually solve for the potential energy itself, for the energy itself, which is your kinetic energy plus your potential energy, which is again g m1 m2 over 2r for your kinetic plus minus g m1 m2 over r for your gravitational potential. What you're gonna get? You're gonna have minus g m1 m2 divided by 2r. So your energy is going, let me just rewrite this equal over here better. So it's minus g m1 over 2 over 2r. So that's your total mechanical energy. So the gravitational force holds us to Earth. It holds Earth into orbit around the sun. It holds the sun together with the stars in our galaxy, reaches out across intergalactic space to hold together a local group of galaxies. It holds together the local supercluster of galaxies. It pulls the supercluster towards the greater attractor, attempts to slow the expansion of the universe, and is responsible for the black holes. So gravity is really, really important. So gravitational attractions depends on the amount of stuff the object is made of. Earth has a lot of stuff and produces a lot of attractions. The force is always attractive and very repulsive. Gravitation is the tendency for those bodies to attract each other. Now, Newton, again, we talked about in the beginning of the lecture, so Newton realizes attraction was responsible for maintaining the orbits of the bodies. Now, Newton's law of gravitation defines the strength of this force between the particles. Okay? Now, it wasn't until, again, Henry Cavendish that we got G, and then it was recalculated, but he got actually really close to it at 1%. So the magnitude of the force is given by Fg m1 m2 over r squared, where big G is your gravitational constant, which is 6.67 times 10 negative 11. So now your gravitational acceleration, where F equals mass times gravity, is going to be your gravitational constant multiplied by your mass of the Earth. This is going to be your mass of the Earth over here. Let me just get this. Yeah. This is going to be your mass of the Earth divided by your radius of the Earth squared. And again, what we got is 9.8 meters per second squared. But again, it's not exactly 9.8 everywhere. There's difference. The higher you can go, the lesser the gravitational force it is, or gravitational acceleration it is on you. The closer to the Earth you go, the higher the acceleration force is on you. So let me just go over here. Yeah. So your force is going to equal, again, to your gravitational constant, G, multiplied by your mass of the Earth, mass of the Earth multiplied by the mass of the object divided by R squared. So the constant density for it, which is your mass per volume, which we just solved right now a little while ago, which is your mass inside the Earth divided by your volume of the Earth multiplied by the distance between them cubed, is going to equal to the mass of the Earth divided by 4/3 pi, the radius of the Earth cubed. Solving it for what we got the force is going to equal to G, mass of the object, mass of the Earth divided by the distance, the radius of the Earth multiplied by the distance between them, which we get to Kepler's law, which is F equals minus KR, which we talked about before. So the object dropped through Earth oscillates, which is Hooke's law, F equals minus K R. Now your gravitational potential energy, which again is given to us in the book as U, so we're going to be sticking with the U. We defined it as, and we actually derived it as minus G M1 multiplied by the mass of the Earth divided by R squared. M1, M2 divided by R, not R squared, R. Again, big M over here, that's your mass of the Earth. I like to call them M1 and M2. And again, the negative sign is because the further you go, the greater your potential energy should be. So when you have a positive sign, it doesn't make any sense because the greater you go, that means it's going down. So you start off from a high number with a negative and it approaches to zero. So your actual potential, gravitational potential energy actually grows larger with distance. So this value is negative as the radius approaches infinity. The bigger the radius are, the smaller the number are, the more that the gravitational potential energy goes to zero. So your gravitational potential energy is actually, again, if you have multiple objects, it's the gravitation between each object. So if in this case between M1 and M2, M1 and M3, and M2 and M3. Now, the kinetic energy, let me just go down to the kinetic energy. Here it is. So your kinetic energy for that, which is you 1/2 mv squared, which is, again, we just derived it as Gm, mass of the M1, M2 over 2R, which is, again, one of the masses of the Earth. That means that your potential energy equals to, your kinetic energy equals to your minus potential energy divided by 2. So it's 1/2 the potential energy. So for your gravitational potential energy, Newton's law of gravitation can be derived from potential energy formula by taking the derivatives. For a projectile to escape a gravitational pull of a body, it must come to rest only at infinity. At rest at infinity, this is your kinetic energy is going to equal to 0, and your potential energy is going to equal to 0 because, again, your radius is actually getting larger and going to infinity. So your potential plus kinetic energy must be at least 0 at the surface. So your kinetic plus potential is going to equal to 0, which is going to equal to 1/2 mv squared plus minus G m mass of the Earth multiplied by the mass divided by R, G m1 m2 divided by R. the radius of the Earth. So solving for the velocity to escape the orbit, you're gonna get 2g m e over r. And that should conclude chapter 13 for physics 111. If you have any questions, give me a call at 256-348-1480, or you can text me, or you can email me at abunaem@uah.edu. Thank you.